I'm Omer, and I'm a PhD candidate at the Technion. And today I will share with you a game-theoretic perspective on recommendation systems or recommendation ecosystems. But before I do, let me very briefly introduce myself. So, as I said, I'm a PhD candidate majoring in data science, but actually this title is somewhat misleading because what I really do in my research is economic theory. So you might ask yourself at this point, what am I doing here in PyData? And to be honest, this is a fair question. And one thing you could do is to go ahead and blame the organizers for letting me sneak in here and, you know, have access to all the swag and food. But before you do, I would like to try and convince you that economic theory and theory in general, mathematical theory, does have something to contribute to AI practitioners. So my main research theme is the intersection between strategic behavior and AI and machine learning system, how these two affect each other and shape each other. And in this particular talk, I will focus on the case of recommendation system. This is based on a joint work with my great collaborator. It was published earlier this year at ICLR, so feel free to check it out now or afterwards. But before we dive into recommender systems, let me tell you a few words about game theory, which is going to be the primary framework through which we're going to study recommender systems. So game theory, for those of you who are not familiar with it, is the study of mathematical models of strategic behavior of rational decision makers. And by rational, I mean that these decision makers are assumed to only care about maximizing their own utility function, okay? And I don't define it formally here, but we'll do it. And game theory has been successfully applied to almost any scientific domain that you can think of, from obviously economics and social sciences to computer science and even biology. And what's common to all of these applications of game theory is that basically what we do is taking a real world scenario, something out there in the real world where some decision makers interact and behave strategically, and we try to capture this interaction by some abstract, overly simplified mathematical model, and then we can, you know, apply some mathematical and analysis tools to analyze it, and hopefully draw conclusions that will then shed light on the core principles that drive strategic behavior and decision making. Now, obviously, whenever we try to capture something complex using a mathematical model, there's a trade-off. On the one hand, we want our model to be complex enough to really capture those real-world complexities, but then again, we want it to be simple enough so we can actually be able to, you know, prove a theorem or analyze it using mathematics. So, as you probably heard many, many times, all models are wrong. We will do our best to come up with some useful wrong model, and this was originally said in the context of statistical models, but this is also true for economic models. So, with that being said, yeah, let's go back to recommender systems. So these are literally everywhere, right? I really don't need to convince this audience that recommender systems really shape the way that we consume and create content across many domains and applications. And I think it's fair to say, or it's roughly accurate to say, that the core task of recommendation is to be able to match end users, the content consumers, with relevant high quality content, right? This is something that's common to at least many of those applications. And this is only one side of such platforms, because on the other side, there are the content creators, those who actually create content, and they have their own incentives, right? They want to maximize visibility, to reach a wide audience, and they even put lots of effort in optimizing their content and, compete with each other. So basically, what we have here is that recommender systems induce a dynamic ecosystems where we have different types of players. We have the end users, the content creators, we have the platform itself, and each of these have its own goals or incentives. So from an economic perspective, this is quite interesting. This is where the fun begins, for me at least. And while there are many economic aspects that we could talk about, and we have some other papers that deal with those, today I want to talk about one particular aspect, which is stability or long-term stability of content competition dynamics. So to illustrate it, let's begin with overly simplified example. So this is our recommender ecosystem. In this huge ecosystem, we have two content creators, let's call them publishers. The content that they produce is the blue and the orange documents. The recommender system chooses to display the blue document to this end user, so therefore the upper publisher is happy and the bottom one is disappointed. So since this is a dynamic ecosystem in which the interaction is repeated, then the day after, the losing publisher could do something to improve their visibility. They could write about a different topic, they could put some effort to improve the quality of the writing, and this way or another, they can modify their document, and now they come up with this brand new green document, which happens to win this time. So now the bottom publisher is happy, and the upper one is disappointed. So no reason to assume that this will stop here, right? I mean, day number 3, maybe the upper one changes its document again, and so on and so forth. So unless they somehow reach a stable state, where I don't know how they're going to reach this state, and I don't even know what a stable state means, but unless something magical happens, these content modification dynamics could repeat themselves for a very long time. And what I claim is that at least for some specific applications, this may cause troubles to the entire ecosystem. And without going into details on why I claim that stability is bad, let me just say that content fluctuations creates uncertainty, which is bad, for anyone who is involved in economic decision-making. People want to be sure about revenue and what their cost translates into in terms of value. And also, for platforms, monitoring supply and demand dynamics is especially crucial. So stability makes these tasks much easier. And in some applications, you might think that fluctuations lead to diversity, which is indeed true, but in many other, specifically in information retrieval applications, being sure about what content is available within the platform is crucial. So once we establish that stability is important, and we want those content creation dynamics to converge in some sense, to a stable state in some sense, this leads us to the following question. So how can we as system designers, or maybe you as system designers, can ensure that those long-term behavioral dynamics will converge to a stable state? And we're going to take a game-theoretic approach to model the interaction, and hopefully using our model be able to shed some light on how should such stable system look like. And we're going to do it in 3 steps. So in the first step, we're going to define what is the model that captures the one-shot interaction between those strategic publishers. We're going to define what are their actions, who are those players, and what are their incentives, what are the utility functions that they try to maximize. Then, once we have a one-shot interaction model, we will define a behavioral model that determines how behavior evolves in the long run. Because if we're interested in stability and convergence of dynamics to a stable state, we need some model that captures long-term behavior. And finally, we'll have to define what is the stability criteria that we want our recommender system to satisfy. So hopefully, once we have these 3 pieces of the puzzle, we'll be able to say something interesting about the stability of recommender systems, at least in our abstract, theoretical, mathematical world. Okay, so we begin with modeling the one-shot interaction. So we have an arbitrary number of publishers, say n publishers. Each of them writes document or any other type of content. And we will think of these documents simply as the embedding representations in the dense embedding space in which the recommender system operates. So this is, it is a simplifying assumption because people don't write vectors, right? They write documents, but let's be mathematicians and say that the action space of the publishers is the entire embedding space. Now, in the same embedding space, we also have representations of the user's preferences, which again is quite standard in dense retrieval paradigms. So we have the user's preferences also represented in the embedding space, and it's taken from some distribution of users. These are being fed into the recommender system, and somehow magically the recommender system produces the exposure rates, the probabilities of exposure for each publisher. Now, the utility of the publisher consists of 2 elements. So the first thing that they try to maximize is the expected exposure rate, where here we take the expectation over the entire user population. But at the same time, they also try to minimize some production cost, which we only assume that this is some concave cost function, convex. Yeah, it's always confusing. But this could very naturally represent deviating from some ideal content that I want to produce unless there was a competition or some effort in producing a diverse type of content. And you can give it any other interpretation. So now let's dive into the black box of the recommender system. So it takes as an input the documents and the user's preferences. First, it computes the distances in the embedding space between the documents and the user. Then it computes relevance scores, where we assume that there is some activation function G. We call it an activation function because obviously this is inspired by some deep neural model behind the scene, but again, we're taking a very abstract approach and we allow for any decreasing function G. So why decreasing? Because obviously we want smaller distances translating into higher relevance scores. And then the exposure is simply proportional to those relevance scores. And this function G captures the entire design choice of the recommender system designer. So at the end, we're going to ask, how should we choose this function G? And this wraps up our one-shot model. And next thing we're going to do is to define how content creation evolves in the long run. So there are many natural ways to define long-term behavior of strategic decision makers. But here we're going to adopt a fundamental concept from theoretical computer science, which is called regret. If you worked with multi-armed bandits in the past, you might be familiar, but let me explain it with no math, just replaced math with sentences. So the regret is defined to be the difference between two terms. The first term is a hypothetical retrospect benchmark, which says what would be the best case scenario, what would be my best reply to the behavior of the publishers if I know their behavior in advance. So each publisher asks themselves, what I could have done had I known the future in advance. So this is why this is a hypothetical benchmark. I don't know the future when I take a decision now. And the regret is simply the difference between this hypothetical benchmark to what I managed to achieve in practice. And our assumption is that publishers behave in a way that tries to minimize regret, and not only tries, but actually succeeds. So in what sense? We are going to assume that each publisher's regret, long-term regret, grows slowly as time progresses. And we don't impose any restriction on how exactly they achieve this objective, because we want to keep our model very general and not restrictive in the way that publishers behave. This is the only assumption that we're going to assume. It is quite general. And let me just briefly say that there is this paper that was published in the same conference that our paper was published, which is cool, that studies the behavior of large language models using these no-regret dynamics theoretical framework. And it's quite cool because publishers obviously use LLMs to create content, so it makes our model quite natural to model behavior of publishers using LLMs. Now, we want to define what stability means in our context. And in game theory, we have a very widely accepted definition for stability in games. So this is John Nash, who proposed the notion of a Nash equilibrium, which is basically a state in the game where no player can deviate, can change its action, and benefit from it, given that all other players remain with their fixed actions. So in other words, a Nash equilibrium is a state in the game where if we somehow reach to this state, then no one has incentive to deviate from it. So therefore, we consider it as a stable state. And in our context, we want to say when a recommender system is stable. So we say that an activation function, which in our model captures the entire design choice of the recommender designer, so this activation function is said to be stable if any no-regret dynamic, and here any is the key word, if any no-regret dynamic converges to a Nash equilibrium. I didn't want to define formally convergence. Believe me, there is a rigorous definition. So this is quite a strong theoretical guarantee, and so we're putting ourselves a very high bar, and now we are ready to at least state our main result. I won't be able to prove it. You'll have to trust me. So if I try to reformulate the research question that we asked before, the question now boils down to, can we come up with some condition, hopefully a simple and intuitive one, that the activation function should satisfy so it will be guaranteed to be stable. And surprisingly, there is a very nice such characterization, which I like to think of as concavity is all you need. So it turns out that under mild conditions, and believe me, they are not so crazy, any concave activation function G is a stable activation function, which basically means that if all we care about is stability, then we need to make sure that the way that we design the incentives for the publisher takes the form of a concave function, which could be, I think, counterintuitive, because many times we think of softmax functions to use in neural networks. So these are made of convex activations. So I think this is an interesting result to practitioners, and also for us, it's quite interesting to have this connection between the mathematical properties and the economic properties. So this is where a mathematician would be satisfied, but we are data scientists or economists, depends on whether it's me or you. So we want to see that there is some value beyond this theorem, and let me just take a very simplified case study just to demonstrate how we can use our game-theoretic model to draw some insights even beyond stability. Because now we know, okay, stability is concavity, that's cool. But let's think of the following case study. So let's say that you just landed a new job in your favorite online platform as a recommender system engineer or scientist. And after this very nice onboarding, the monetization lead pulls you aside and tells you that, you know what, users love the content in our platform, but the publishers are really unhappy, and they could be at risk of leaving to the competitor platform. So this is kind of your first task. So in order to explore this, and in order to better understand this, let's say that you meet with your ML scientist and asks about the current recommender system, and they tells you that our mechanism, our existing mechanism could be more or less approximated by something that is driven with this activation function. This is a concave function, which is good. It means that our system is stable. But still something about the balance between user and publisher welfare is bad. So when you think about it a little bit, you realize that this activation function could be seen as a part of a broader family of activation functions with this parameter A, which is the power of the 1 minus D. And as long as it's between 0 and 1, then this is, again, a concave function, which is good. But a very natural question to ask is, how varying this mechanism parameter A affects the users and the publishers' welfare? So one thing that you could do is to simulate no-regret dynamics, to simulate the prediction of our theoretical model. And we actually did it in the paper. And we could plot the publisher's welfare and the user's welfare as a function of the parameter A. Okay, so this is based of lots of simulations. I don't have time to go through the details. But one thing you could do is that the publisher's welfare decrease with A, and the user's welfare increase with A. So if we need to compensate the publishers, we could slightly decrease the parameter A, but of course this comes at the expense of the users. So it needs to be handled carefully. So this is just a very simplified use case, but I truly believe that there are more. And let me just conclude with a final thought from a theorist's perspective. So I wonder what is the role of theory, not only economic theory, but generally speaking theory in AI research and development of real systems. And I really think that as we tend to use those very powerful yet unpredictable tools of LLMs, GenAI, and especially agents, then those systems become really hard to anticipate. And maybe theory could guide us. Now, obviously, it couldn't perfectly guide us, but I think it could be a very decent starting point. And I really think that developing theory and applications together in parallel could be mutually beneficial. So if anyone finds this interesting, I'll be happy to chat. And I hope that it was somewhat useful. And thank you.